Right. So I guess it's actually in the kind of tradition of SPICE conferences that some subset of the organizers give a kind of tutorial talk to maybe just give their perspective of the field to kind of normalize language and so on. So I'll take that opportunity here to talk about some set of quantum optics, which is about quantum optics primarily with atom arrays, and exploring the effects of collective dissipation in these types of systems. So I should say that I actually have quite a bit of time for the tutorial. I certainly don't have that much content. And so also in the spirit of a tutorial, if you have any questions, just feel free to interrupt. And hopefully at the end, I'll have enough time to actually just kind of pose what I think are some interesting questions and future directions for later discussion. OK, so I thought in the tutorial I would try to cover three very general but important questions. So in quantum optics, why might we care about collective effects and collective dissipation? And then I'll talk about actually novel paradigms, some of the ones that we know so far, to realize processes of interest, let's say for quantum information processing, that explicitly utilize collective dissipation in atomic systems. And then at the end, I'll also try to cover what we don't know yet about the field, which I think really is still a lot of things. But I think that's actually where the most exciting frontiers lie at the same time. And this is kind of roughly also based on complexity of the system. So you have a collection of atoms, you can shine in light, you can excite one atom, two atoms, and so on. At the level of ones and twos, I think we have at least some idea of why collective dissipation is useful and how we can encode interesting effects or applications in atoms. And then the question of many is very closely tied to what we don't know. So I think what needs no introduction is that people all over the world are experimentally trying to implement efficient atom-light interfaces, which means you shine in resonant light that's near resonant with atomic transition. You hope to induce some kind of efficient interaction with the atoms. And if that interaction is coherent enough and if you can control it, that leads to applications like quantum memories for photons, where you can basically take a kind of photonic qubit and then store it in a reversible way as an atomic excitation and then retrieve it. Photon-photon entangling gates, quantum metrology or sensing, things like magnetometry with atoms or spin squeezing, et cetera. And so at the risk of kind of overgeneralizing, I think probably the kind of simple message is that in experiments today, people can more or less do all these things, but probably not nearly as well as they would like to. Okay? And there's an underlying challenge to all of this, which is simply that a single photon and atom don't naturally interact very efficiently. And one kind of very simple figure of merit to capture that is if you were to hypothetically take just a single atom and take resonant light, so light that's resonant with an atomic transition, focus it down to some area A, you can ask what's the probability that a single photon in that beam will scatter off that single atom. And there's a simple, well-known formula that the scattering probability on resonance is actually just given by the resonant wavelength of the transition squared, divided by the beam area. And the problem in free space is that you have a diffraction limit, so you can't make this area arbitrarily small. And that combined with kind of technical difficulties, if you really try to do this experiment, you'll get to 10% coupling efficiency, more or less. But what you want is 100%. So if you can achieve 100%, then in principle you can do all these things arbitrarily well. And so the problem I mentioned is not a mysterious one. People have known that for forever. And then at least in kind of atomic physics, one common approach that people have used to try and fix that is simply to use more atoms. So the simple picture is that now you have a photon coming in. If it doesn't manage to interact with the first atom, it can interact with the second. If it misses the second atom, it can interact with the third. And so then your interaction efficiency or probability scales with the number of atoms. That parameter in quantum optics jargon is known as the optical depth of your medium. And there's actually kind of complementary viewpoint of this picture. So here I thought about efficiency in terms of a single photon coming in and trying to interact with the atoms. You could also say, well, what if I have a collection of atoms, and I have one of them excited, but I'm allowed to kind of distribute that one excitation in some kind of arbitrary superposition across the n atoms. So then it turns out if you put the proper phase on that excitation, so e to the I kr, then it turns out that you'll get a kind of collective enhancement or constructive interference of light emission in the direction that's set by k. So in fact, even though you have one excitation, the efficiency that you get to kind of send the light into your preferred mode or direction grows with atom number. Whereas the emission in a free space into 4 pi directions that you generally can't collect, that still stays the same. And then it turns out that the branching ratio of light that you kind of get out in a good mode versus bad is exactly the optical depth. And so once you realize the optical depth is this kind of branching ratio of information, you have an excitation or some kind of quantum information stored in your atoms, and D sets the probability that you get it out versus you lose it, then it kind of makes sense that D is really a fundamental parameter, which should set fundamental limits on how well you can carry out any application. If you want to kind of just a classical picture of what this collective enhancement is, you can do a classical simulation where you have radiating point dipoles. You assign all of them a phase, e to the IKR, and then you really see, if you calculate the total field, this kind of constructive interference in the forward direction. Okay? So I try to argue abstractly that optical depth is important. Let me just give a kind of more concrete example of that. So imagine you want to implement a photon-photon entangling gate. So there's different variations of protocols, but a typical one kind of looks like this. The first one is you take your first photon and you shine it into your atomic medium, and you try to do a quantum memory or photon storage. So you start with all your atoms in the ground state, you shine in one photon, that takes one atom up to an excited state, if you can perfectly absorb it. And then what you can do is, instead of just leaving the atom in the excited state, you can transfer it to a long-lived high-lying Rydberg excitation. Okay, so at the end of this process, ideally, this one photon gets converted to one Rydberg excitation somewhere inside your medium. And it's known that the error of this process, of this storage process, scales like 1 over optical depth. Okay, so this sets the probability that instead of getting this red dot in the middle of your ensemble, you have no excitations because you lost the excitation to somewhere else. The next thing you can do is you can send in a second photon. And the trick is that if this first excitation, if this first photon was converted to a Rydberg excitation, that high-lying Rydberg level can impart very strong dispersive interactions on all the nearby atoms. So you can shift the resonance frequencies of all the nearby atoms, or in simpler language, change the refractive index of some nearby region. And then when you send in a second photon, that second photon can, for example, pick up a conditional phase shift depending on the presence of that first excitation. And the error of that depends on, again, the optical depth, not of the entire ensemble, but just of this region, this so-called blockade region, which this first Rydberg excitation is able to modify the optical properties. So this is really just to kind of illustrate the optical depth really does enter in as a fundamental error limit. The problem, though, is that if you really try to do this in an experiment, the best experiment so far for a photon-photon entangling gate has an error of around 60%. Okay? And so that's kind of one reason why you never hear of photon-photon entangling gates or photons and atoms as a competitive platform for quantum computing, as opposed to superconducting qubits, ions, et cetera. Okay? And the fact we're sitting at 60% despite lots of effort to improve it really just kind of suggests that it's very experimentally hard. And so it really motivates asking, is there some way to do better? So to try to figure out ways to potentially do better, the first thing that you should actually ask is, how do I arrive at these physical conclusions in the first place? And what is the underlying theory? And so if you're not from the field of quantum optics, you think of atom-light interactions or quantum electrodynamics as actually something very fundamental. Right? Maybe you write down Hamiltonians, you solve it exactly, et cetera. But then I'll try to convince you that that's not really possible. Okay? So particularly if I have an atomic ensemble, I might have something like 10,000 million atoms. And if each one is a two-level system, you're talking about a Hilbert space that's immense. And more or less, you have atomic positions. They could be moving around, et cetera. And then when you shine in light, that can have any frequency, direction, photon number, et cetera. So that's also an infinite dimensional Hilbert space. And so when you have this Hilbert space that's infinite times infinite, you see that there's no way to construct any practical microscopic theory. So it turns out then when we deal with atom-light interactions, at least for ensembles or practical settings, you have to make approximations. And the approximation that people make is very closely based on our foundations of classical optics. So just as an example, if I have a piece of glass is actually amorphous. So there's 10 to the 23rd degrees of freedom, which are random. But then when we open up an optics book to understand how a prism works, we're not solving 10 to the 23rd equations. Why not? Because in optics, we say that the microscopic properties are somehow more or less decoupled from the macroscopic optical response. So the macroscopic response is only tied to a single number, the refractive index. And once I know the index and the shape of the prism, I can tell you perfectly how that prism is going to behave. So in conventional quantum optics, we basically did the same thing historically. We say that in principle, we have a collection of point-like atoms, two-level systems. But then the granularity or microscopic properties of these atoms shouldn't really matter. So at least in terms of light, we can kind of smooth that over into a uniform medium or a uniform quantum field. And so then the interaction between light and matter becomes some smooth, abstract quantum field theory. Okay, so basically just to summarize, our standard textbook equations throw out granularity. And then you might ask, what's really the physics associated with granularity and optical interactions in the first place? And it's not hard to believe that what's associated with granularity is multiple scattering of light and wave interference, which has to depend on microscopic properties like the positions of the atoms, et cetera. So that's not a deep statement, but it can be really rich or non-perturbative once the distance between atoms becomes smaller than the optical wavelength. So then the picture is that the kind of scattering cross-sections of different atoms start to overlap with one another, and then that can lead to non-trivial effects. What's important in terms of the kind of cartoon picture I presented earlier is that when you have wave interference, you realize that the light emitted into 4 pi, which you say you're losing and that you don't want to occur, is a wave interference phenomenon. Right? To calculate the far field energy, I have to account for interference from my sources, which are the different atoms. And so then essentially by conservation of energy, you're forced to conclude that this kind of picture of independent emission. So if an atom is excited, it's going to emit into 4 pi at a rate that doesn't depend on any other atoms or microscopic details. That fundamentally cannot be correct. So the true model of atom-light interactions has to, and in particular this kind of emission into 4 pi, has to be a story involving correlated emission or correlated dissipation. Okay. So then the question is, can we exploit wave interference in protocols? So I'll present this kind of deeper theory and in equations later, but I want to just kind of present the basic picture here because I think it's very simple to understand conceptually. So if you want to build an atom-light interface, which is efficient, again, you basically want to guarantee that anytime a collection of atoms is excited, it always emits into your good mode and never emits into 4 pi. And so our standard textbook theory guarantees this kind of collective enhancement into the good modes, but it says that interference into 4 pi doesn't occur. And then the true story is, well, if we can somehow exploit correlated dissipation or wave interference, maybe I can use destructive interference to shut off that 4 pi emission. And if I'm lucky, maybe the rate at which I can shut it off actually depends on atom number. So as I have more and more atoms, I can shut off 4 pi emission more and more efficiently. And so then if I try to naively define a branching ratio, which is, again, the emission into good quasi-1D modes versus bad emission, if this denominator is shrinking very fast as a function of n, all of a sudden I can hugely beat these kind of naive optical depth limits that exist in textbooks. So this is a concept that's coined selective radiance. There's another aspect which is called subradiance. where the statement is that if you really allow for wave interference, maybe there's kind of non-trivial settings in free space where you can shut off emission into all directions. And in that case, when you can't dissipate, the coherent interactions, no matter how weak they are, will eventually accumulate. And if they accumulate for a long enough time, that might eventually drive you into some kind of interesting, strongly correlated state. So that's the reason to really explore correlated dissipation in atom-light systems. So there's a lot of theory on this, going back to kind of pioneering work by Helmut Rich. There's actually also a growing number of experiments to observe signatures of this types of physics, either in real atomic systems, with solid state atoms with optical transitions, or even in the kind of microwave regime with superconducting qubits. Okay, so now I'd like to describe how we might come up with a model that formally encodes wave interference and multiscattering of light. Again, I kind of argue that a microscopic theory shouldn't be possible. On the other hand, if we need granularity to capture multiple scattering, it kind of becomes clear that we can't really touch the atomic part of the Hilbert space. So then kind of, even though it sounds kind of counterintuitive or weird, the only option you really have left over is to throw out the light. Okay, so we're going to talk about atom-light interactions by throwing out the light at the very first step. To kind of convince you that actually isn't as weird as it sounds, here's a kind of typical problem that we might want to solve. So we have a collection of atoms. We shine in light whose properties we assume we know. That light will start to excite atoms. When the atoms are excited, they can emit a photon, but that photon can be reabsorbed by another atom and multiply scattered. And then at the end of the day, we want to calculate, we imagine we have some hypothetical quantum detector, and we want to calculate any quantum property of the light, any correlation function, as a function of space and time. And then, in terms of what I mean when I say atom, I'll really, for the purposes of this talk, have some minimal model in mind, a two-level atom with an electronic ground and an electronic excited state, which are connected by an electric dipole transition with some well-defined transition frequency, omega EG. And then gamma naught is what I'll call the kind of single atom spontaneous emission rate if that atom was really isolated and far away from any other atom. So it turns out to be formally easy to kind of get rid of the fields, because formally you can always say that your total field is the coherent sum of what you send in, and the field which is emitted or rescattered by your sources, in this case, the atoms. So I think all of us know that that type of relation is true in the classical regime of optics. It turns out to be true in the quantum domain as well as a kind of quantum operator equation. In this case, when we talk about two-level atoms, our sources are really encoded in the lowering operators of my two-level systems, or the atomic coherence between the ground and excited states. So this function g here, this electromagnetic Green's function, just basically tells me how a field propagates from some point-like source sitting at Ri out to my observation point R. And so as long as we're talking about free space, this is nothing more than the kind of famous lobe radiation pattern of an oscillating dipole. And then the important thing about this equation is that you realize that the total field is not really independent degree of freedom. If I know what I send in, and I know all the properties of the atoms, I can go and construct any correlation function of the fields for free. So then I have to figure out what actually are the atoms doing. And so kind of mathematically or abstractly, you can imagine that if I started from a full Hamiltonian, when I were to write down Heisenberg equations for the atoms would be driven by the light. But because I can write the light in terms of input field and the light scattered by other atoms, then the equation of motion for the atoms can be captured just by an effective Hamiltonian, which contains my input fields and other atoms alone. So I've reduced my system to a pure atomic description. So this form of a Hamiltonian, if you're not familiar with quantum optics, might look abstract, but it contains pretty intuitive physics. So this form of interaction here is basically like a population exchange. So if one atom J is excited, another one is in the ground state, this Hamiltonian allows atom J to drop down to the ground state and atom I to get excited, physically through photon emission and reabsorption. And then intuitively, the strength of that interaction depends on the Green's function, or how a photon propagates between my two atoms. So besides the possibility of getting coherent dipole-dipole interactions, when you integrate out the light, you also get the possibility of correlated emission. And so you get a kind of density matrix equation now for your atoms. The specific form of this master equation doesn't really matter going forward. The only thing to point out is that this kind of dissipation term contains a sum over atom pairs. Okay, so that encodes the fact that wave interference governs the emission of atoms, and then my dissipation has to be correlated rather than independent. Okay, so my claim is that this Hamiltonian here and this master equation here fully encode atom light interactions into some kind of exotic spin model. Okay? And it's exotic in the sense that abstractly spin models exist in condensed matter. They've been solved or investigated forever. But this kind of particular spin model has some interesting characteristics. The coherent interactions can potentially be long range. We're interested in out of equilibrium dynamics because we have to shine in light and kick atoms into excited states in the first place. And then we have kind of long range correlated dissipation as well. So it's a kind of interesting set of ingredients, which makes it kind of a little bit non-standard compared to normal spin physics in condensed matter systems. Okay, so that's the kind of model or one possible model that you can use to talk about correlated dissipation in quantum optics. And now what I'd like to do is just kind of present some of the simple physical consequences and what we can do exploiting collective dissipation. So the first effect that's kind of neat is that if you create it turns out if you create a 2D array of atoms with sub-wavelength lattice constant, then when you shine in near resonant light, that array of atoms can act as a perfect mirror for single photons. So to qualitatively understand that, there's just 4 ingredients. Okay? So just to kind of make it concrete, let's imagine that we shine in light at normal incidence. So the first ingredient is to realize that isolated atoms cannot absorb a photon. Okay? So a 2-level system has no other degrees of freedom to just eat that energy and make a photon disappear. So when you have an atomic system, you shine in a photon, you'll always get it out somewhere, even if you can't detect it. The second ingredient is that when you have this kind of spatial order, that photon can't scatter into a random direction because this atomic array basically acts as a diffraction grating. So you can also scatter in discrete diffraction orders. So for example, you can have a fundamental diffraction order where you shine in light and it either goes straight down, which is transmission, or comes straight back up, which is reflection. And then you can have a first diffraction order where the atomic array adds 1 unit of reciprocal lattice momentum to the photon. And so then the photon comes out at a well-defined angle. The third ingredient is to realize that when you make the lattice constant smaller and smaller, this kind of first diffraction order, or the momentum associated with it, gets bigger and bigger, right? Because it's 2 pi over d. So at some point, this momentum gets so large that a photon can't even accommodate it anymore, right? Because the photon is a fixed momentum of omega over c. So once you make the lattice sufficiently small, in particular when the lattice constant is smaller than lambda, it turns out that only these fundamental orders are radiative. And then the last ingredient is that atoms have a resonance. Okay, so in other words, in this kind of cartoonish picture that I presented before, a single atom has a cross-section of lambda squared. So when d becomes smaller than lambda, it's not really possible that you shine in light and then the atoms just don't even have an effect. The atoms have to have a very appreciable response to the light. And it turns out that appreciable response turns out to be 100% reflection. So this has actually been experimentally observed in Emmanuel Bloch's group at MPQ. So basically what they do is they create a Mott insulator of atoms in an optical lattice. So it's essentially a defect-free 2D array. And then they can just do a simple optics experiment where they shine in near resonant light. They have a CCD detector to measure the reflected field. And you really see a kind of high reflection exactly where this Mott insulator is sitting. So if you like the numbers, they don't exactly get 100% reflectance. They get 60%. That's not really due to anything fundamental, but it's more mostly actually because I think the experiment was not really built as a quantum optics experiment, so they're not really able to kind of shine in light and collect into good modes. Okay, so if you build a mod insulator to create a mirror, that's a very expensive mirror. But then you can ask, well, what if I try to functionalize into something that's a little bit more quantum? So in particular, you might get excited because you would say, well, maybe 100% reflection is actually a signature that I have 100% atom-photon interaction efficiency. And that turns out to be true, but before you get too excited about that, you should realize that even in textbook models, if I have an infinite number of atoms, then my optical depth could be infinite, so I have infinite resources, and then I can also do everything perfectly. So the real argument to make is not when you have an infinite system, but when you have a finite-sized array. So let me actually talk then about what efficiency really means in a kind of experimental sense. So again, the point in optics is that we don't know how to kind of create light in arbitrary modes in 4 pi, nor do we know how to detect light in arbitrary modes in 4 pi. What we do know how to do is create light in simple modes like a Gaussian mode. Okay? So in an experiment, you can easily create some kind of Gaussian mode, and you can ensure that that Gaussian mode impinges on some finite array. Once you've created that Gaussian mode with the same optics, you can detect any light reflected, but only back in the same Gaussian mode. And you can also align optics to detect any light that's transmitted in the same Gaussian mode. And of course, these kind of two Gaussian modes in transmission and reflection are just two discrete electromagnetic modes out of an infinite set of modes forming your continuum. And so then in optics, or in quantum optics, what we say is that, of course, these are just two modes. There are other modes. But if light does manage to scatter into those other modes, for all practical purposes, we can consider them lost as 4 pi emission. So then if you have a kind of finite-sized array and you want to get high reflection, it's kind of clear that there's two errors you can have. If you take your incoming beam and you make the beam waist way bigger than your system size, most of the beam will clearly just transmit through, not knowing that the atoms exist. If you try to focus your beam so tightly that it only touches one or a few atoms, then all your collective effects and interference effects have to disappear. And so there's a kind of optimum there. And it turns out that then you can calculate the reflection maximum, and then the error goes down pretty quickly as a function of increasing atom number. Okay, so then you can actually try to functionalize the system. You can say, I'm going to try to turn my finite-sized array into a quantum memory. And again, what a quantum memory is in some abstract sense is that you have something like a single photon or a single photon qubit. You want to map that through some unitary process into a collective atomic excitation, and then have the ability later on to map it back coherently into a photon. So here's kind of how a quantum memory protocol might work when you have an array. The first thing you do when you have this single photon is you should split it on a beam splitter and send it in symmetrically onto the array from both directions. That kind of makes sense because the atomic array has a mirror symmetry, so it naturally wants to couple to light that's sent in symmetrically. So then if you shine in a single photon, that photon ideally would make one atom from the ground state jump up to the excited state. That excited state, if you just left it alone, would of course re-emit the photon right after it got excited. But then what you can do is you can add an extra control field, classical beam, to kind of shelve that excitation into a high-lying and long-lived Rydberg state. So at the end of the process, you've achieved this unitary process where you've turned that incoming photon, into a collective excitation of one Rydberg atom somewhere in your array. And so, without going into details, it's kind of intuitive that a quantum memory would have exactly the same error sources as kind of reflection, so you can't make your beam too big nor too small. And so the error of this quantum memory actually scales with linear atom number as 1 over n to the 4th power, okay, which is a pretty strong scaling with increasing atom number. So aside from abstract scaling, you can actually also look at numbers. So if I look at the linear size of my system n on the x-axis and compare it to the error of my memory on the y-axis, what I notice is that already for very small arrays, a 5 by 5 system, that already gives me down to 1% errors or less. Okay? So it seems that the idea of using constructive and destructive interference to your advantage has a very big effect once you move to atom arrays. And then if you're being greedy, you can say that you can realize that actually this kind of polynomial improvement over the textbook answer isn't even fundamental. So I won't discuss it any further, but if you change the geometry a little bit, you couple atoms to, for example, a one-dimensional optical waveguide, you can actually make the error exponentially small in the optical depth. Or to say another way, what the textbook said was the fundamental limit is actually exponentially incorrect. You can do exponentially better. And so this result kind of came out a few years ago, but to me that really kind of piqued my interest because it's a simple effect, it's one excitation, but if our understanding is already so incorrect at that level, what actually is the true boundary of what we can do with atoms and light, especially once we use collective dissipation? Okay, so a quantum memory is basically a single photon effect. It's also passive, in the sense that all I'm doing is if you give me a photon, I'm going to store it for some amount of time and give it back to you. So if you gave me something that wasn't quantum in the first place, I wouldn't be able to generate anything quantum for you later on. So to make the problem a little bit more rich, what you'd also like is maybe some functionality to generate quantumness or generate entanglement between photons. And that could take the form of a photon gate. And a gate is also easily implementable with these types of atom arrays. So the idea is that the first step would be exactly the same. You shine in a photon, you do a storage, so that your incoming photon gets mapped to a Rydberg excitation. And then once you do that, you can utilize strong Rydberg-Rydberg interactions. So that, for example, if this one atom in the array was promoted to a Rydberg state, you use strong Rydberg interactions to essentially affect all the atoms in its vicinity. So you can try to shift, for example, the resonance frequency of all the atoms in the vicinity. And that means when you shine in a second photon, that second photon sees this blockaded region effectively as a giant hole that's punched into your mirror. So what that means is that depending on the presence or absence of that first photon, if you changed that photon number into a conditional reflection or transmission of your second photon. So that entangles the photon number in the first pulse with the direction of the second photon, but then you can kind of, with then classical optics beam splitters, turn that into a true photon-photon gate. And not surprising, for that gate to work, you simply need that the kind of hole punched by your first photon is bigger than your beam waist. Okay, so that your photon really kind of fits through the hole instead of getting scattered off the boundaries. And so maybe not surprisingly, the error of that photon gate also scales like 1 over, in this case, the blockade radius to the 4th power. And then if you put in numbers, if you're able to blockade just even a few sites, which certainly is possible experimentally, again, that gets you to a gate whose error is less than 1%. So if you care about abstract scalings, this kind of 1 over Rydberg blockade to the 4th power is a significant improvement, again, over what textbooks said was the best answer possible. So far when I said that you can get the errors about 1%, I'm only talking about kind of fundamental errors due to kind of scattering into 4 pi and how much you can suppress it. You could ask, what are the kind of extra experimental imperfections that you might have to deal with? So for example, in real life, these atoms would be moving. I might not have perfect filling, et cetera. But realistically, I believe that these errors could also be at the 1% level. So in short, I think these kind of atom arrays are a pretty promising system to really achieve high efficiency and high fidelity quantum gates for photons. So again, at least some aspect of this physics has also been experimentally observed, again by Johannes Zeyer and Emmanuel Bloch's group. So again, they start from the same type of system, a Mott insulator in a 2D quantum gas microscope. They see that if they just prepare the Mott insulator, they can get perfect reflection or very high reflection. By playing some simple quantum optics tricks, instead of making your 2D array perfectly reflecting, you can also make it perfectly transparent. And then what they do is they don't send in a single photon to realize a gate, but what they do is just kind of classically, they pick out one atom in the array, they flip it into a Rydberg state, by hand, and they want to see that that one flipped atom into Rydberg state has a huge optical response when they shine in light afterwards. So that's kind of illustrated here. They take one atom in the middle, they flip it to Rydberg state, and you see that this kind of previously transparent atomic mirror now becomes reflecting in some substantial spatial region. Okay? So I think these kind of experiments, even though it's not a photon-photon gate per se, are quite promising in illustrating that these ideas should be implementable with realistic technology. Okay, so far I talked about quantum memories and then photon-photon gates, which are a story of 1 and 2 excitations. I'd now like to at least present maybe a partial or very limited view of what the story might be when you have many excitations. And to do that, let me actually just go back to the single excitation case in this 2D atomic mirror. And let me present the physics in a slightly different way. So if I have just one excitation in this atomic mirror, and if it's an infinite 2D array, then I should be able to diagonalize my system, my entire, both my Hamiltonian, but also my entire master equation by Bloch's theorem. Okay, so all my eigenstates should be well-defined spin waves where one atom J is excited with a phase e to the ikr, and this k here is basically my Bloch momentum. So just by utilizing the discrete translational symmetry of the system, states like these are guaranteed to be eigenstates in the single excitation manifold. But then because I have a kind of open system, I'll get a complex dispersion relation. So each Bloch mode k will have not only a real frequency component, which is what you would call the kind of conventional band structure, but also a dissipative component, gamma, which is a function of k itself. And what's kind of more important going forward is not the kind of real dispersion relation, but actually just the imaginary part. So here what I'm doing is I'm plotting gamma of k in the first Brillouin zone. So kx and ky have to be less than pi over d. And you see a kind of interesting feature pop up. So first of all, when we shine in light at normal instance and look for this reflection, what we're doing is we're shining a k equals 0 mode. Okay? And you see that for k equals 0, there's a non-zero emission rate of this spin wave. But then basically because of this kind of translational symmetry, we know that all that light is kind of reflected back into the direction that you sent in. So this is just another manifestation of this selective radiance phenomenon. Aside from that, though, you notice that there's a kind of a discontinuity of this kind of circle. So there's a set of Bloch modes which have a non-zero decay rate. But then if the k vector, the magnitude of the k vector, becomes bigger than omega over c, you see this decay rate goes to 0. Okay, so this atom array has one excitation, but at least in theory, that one excitation can live in there forever. And the reason is pretty intuitive to understand. So when the spin wave k vector is bigger than omega over c, that doesn't match the dispersion relation of light anymore. So it doesn't couple to radiation waves, and the excitation has no choice but to stay there in the system indefinitely. So then you can ask, well, so the same as long as you have a subwave from the array, these exotic subradiant modes are automatically there in your system. But then you kind of come across a kind of conceptual question, which is how do we access these subradiant modes if they decouple from light in the first place? So for example, the way I typically try to excite atoms is to shine in laser light. Laser light, no matter what direction I send it in, is by definition a radiation mode, and that should decouple from these subradiant states. So there's been a number of different ways proposed to try and access these subradiant states. For the purpose of this discussion and getting to many-body physics, I'll mention one of them, which is to maybe use interactions. So in particular, imagine that we had an array of atoms, and I created two spin wave excitations, or wave packets, which had k vectors k and k prime. So if these were harmonic oscillators, or like an optical fiber, of course these wave packets would just cross each other without doing anything. But because I have two-level systems, a two-level system can't get excited twice. So if these wave packets were to hypothetically collide, they would have to interact basically through the hardcore nature of my spin. And so what that interaction does is it can impart momentum to each of these k vectors. So this could turn into k plus q and k prime minus q. And then you can kind of qualitatively see how it might be possible to access these subradiant states. So even if k and k prime were initially radiant, so they lived inside the light cone, this scattering process could cause this to scatter outside of the light cone into these subradiant modes. So then, one thing you can look at numerically is, well, let's just try to excite subradiant modes by exciting a bunch of atoms at once. So for example, we can initially even invert the entire atomic array. I'm sorry, I should say that, so for the purpose of numerics, we switched a little bit from a 2D array to a 1D chain just to get something closer to a thermodynamic limit. Okay, but the overall physics doesn't really change. And so what I'm showing here is like the excited state population as a function of time for increasing atom number from 6 to 30. Okay, so you generally see kind of at early times when you have so many excited atoms, a lot of these modes are radiant, the system will very quickly shed excitation, so the number of excited atoms goes down. But in a long time, you see a kind of a lot of population, excited state population hanging around. And to quantify that, you can take these same plots and replot it on a log-log scale. And what you see at long times numerically is that the population doesn't even decay exponentially anymore. It decays as a power law. So it's like there's some kind of critical slowdown behavior in the system. Or to say it another way, what seems to be happening is that you have a closing Liouvillean gap. So you have a master equation, or Liouvillean. But then it turns out that as you grow the system size, as n tends to infinity, even though your true ground state is kind of all atoms in the ground state, you're going to have a lot of metastable states whose lifetimes approach infinity. And these metastable states are not necessarily only single excitation eigenstates anymore. They can actually be many-body excitations. Okay. So this kind of critical slowdown is one interesting effect that we see at the many-body level just from numerics. Actually, another interesting effect is when you look at as a function of time, you can actually look at not just population, but density-density correlations. So in other words, if I know that atom M is excited, what do I know about the relative probability of another atom N being excited? So what I'm plotting here are different snapshots of these density-density correlations as a function of time evolution. So at early times, you basically see it's featureless. Okay, so one atom being excited doesn't tell you about another atom being excited. Along the diagonal, of course, this is 0 because a single atom can't be excited twice. But then as you see as time evolves, you see this kind of feature along the diagonal getting bigger and bigger, which means that when one atom is excited, it's then increasingly unlikely that a nearby neighbor is excited at the same time. So if you want to be a little bit provocative, you could say that maybe some type of fermionic behavior or Pauli exclusion is dynamically building up between excitations as a function of time. And it turns out that, so you can come up with a more careful argument, but it turns out a cartoonish argument is sufficient to make that plausible. So the point is that imagine you have, in this case, two excitations, k and k prime, where k and k prime individually, if they existed alone, would be subradiant. But then once they collide, I know that I can exchange momenta. And then it's possible that these two subradiant states upon collision would scatter themselves into radiant states and disappear into 4 pi. Okay, so these types of states should not be allowed a long time. If I want some combination of subradiant states that persist at long time, I actually should make sure that they can't scatter off one another. And mathematically, I can do that by expressing a wave function as a Slater determinant. So if I take these two single particle wave functions and build a Slater determinant of a 2-particle wave function, then I build in some kind of Pauli exclusion, which physically forbids this collision. And it turns out these kind of Slater determinant wave functions are what dominates these density-density correlations at long times. So that's a kind of interesting effect. Many body subradiant states, apparently, in these 1D chains have some type of fermionic character, very roughly speaking. So with that, I'm basically done. So maybe just to summarize, independent spontaneous emission seems to be a killer for a lot of applications that people want to do with atoms and light. On the other hand, we know that the true model for atom-light interactions can't be independent in nature. It has to be correlated. So I introduced a kind of correlated spin model that in principle captures that physics. And then in terms of simple applications involving 1 and 2 excitations, it seems like encoding applications in this protected space really leads to significant improvements in errors. And then that leaves the many-body frontier. Okay, so I spend a lot of time talking about 1s and 2s. I try to give you a flavor of some many-body physics that we know. And it's kind of one of a few examples, but I think that one example is very representative. Okay, so it's one example that I cooked up for a random reason. You can do numerics, and you can find something interesting that happens. After the fact, you can try to develop some rough intuition for it, but that's kind of where it stands. And so I think in the future, one big kind of objective of this field, and certainly one of my own objectives, is to go beyond 1s and 2s and really into this many-body frontier. For example, from an application standpoint, to encode any application you want into a space that's protected by correlated dissipation. So this could be a many-body application like spin squeezing, for example. And also in this kind of many excitation regime, to really look for new strongly correlated phenomena and states. And this kind of many-body example I gave you before is kind of one small step along that route. So I think it's a kind of very complicated problem. And I think to kind of make progress on it, you need probably several different things to happen. So first, I think you need some kind of insight-based development of new theoretical and numerical tools to throw at this problem, because exact diagonalization will not get you very far, probably. I think also instead of thinking about just isolated examples and intuition, I think it'll really benefit to be able to think about this type of problem at a more broad level in terms of paradigms and universality classes. I think it'll also be pushed by experimental efforts, so the development of dedicated experimental platforms to explore this physics. And finally, which I think is also I hope one of the kind of outcomes of this conference here, is to find inspiration from and connections to other fields. So particularly in quantum optics, I don't think we're very well trained to think about spin models and dissipative spin models. And I think that's where rather than kind of living in a closed box, talking to people from other communities and getting their input will be very helpful. So with that, I'm done, but I'm happy to answer any questions that you have.